Alrighty, here we go. Here are the notes for 7.3 logarithmic functions. So we're going to start with just sort of the definition here. The definition of a log: let a be a positive number with a equaling 1. The logarithmic function with base a, denoted by log base a, is defined by, and we have this logarithm here that says log base a of x equals y. Say that again. In this form, it's read, the log base a of x equals y. Now that's the logarithmic form. There are two forms. They're inverses of one another. The other guy, the exponential form. So given this log, it translates to the base a to the y power equals x. Therefore, the logarithm is an exponent. Why do we have logs? Well, we know that we can solve 4 to the x equals 64. In that case, x would equal 3, 4 to the third power equals 64. But what if we had 4 to the x equaling 53? We would run into trouble. So logarithms will help us solve this problem. So let's take a look. Let's jump right into this. Okay, we need to know how to be able to go from exponential form to logarithmic form and vice versa. So we're going to use what we call the log loop. You will hear that term often. The log loop, not a technical term, it's just something that we've come up with that helps us go back and forth from one form to the next. So, how do we implement this log loop? Well, you start with your base. The base in this logarithm right here, the base in this logarithm is a. And we say that the base a, and here comes the loop, to the y power, a to the y power, is equal to, and we continue the loop. The of component in this case is x. A to the y equals x. So we will be going back and forth from one form to the next. And to go from exponential back to log, you again start with your base, because if you notice, the base of the logarithm is also the base of the exponential form. So you start with the base, you say log base a, and then that of component, when you go to the log loop, the y in this case is your exponent. That's why we say that the logarithms are exponents, because y equals the log base a of x. So you put your y up in the exponent, and then you set it equal to x. So let's do this here. Now that we know how to rewrite logarithms as exponential functions, we can now evaluate expressions like this. The log base 4 of 1 over 16. Well, we're going to figure out what it equals. So the first thing we'll do is set it equal to x. We'll rewrite as an exponential equation. So the log base 4 of 1 over 16, that equals x. Now, knowing what we know about our log loop, we can rewrite 4 to the what power, in this case x, equals 1 over 16. And now we have an exponential equation that we learned how to solve back in section 7.2. We need common bases, and with 4 being my base and 1 over 16 on the other side of the equal sign, I can recreate common bases, and therefore x equaling -2. Whoops. And so, when we're asked to evaluate logarithms, we can say that, hey, the log base 4 of 1 over 16 is equal to -2. It's just simply asking you, hey, what power of 4 do you need to raise it to in order to get 1 over 16, or that of component? It is essential that you are able to move between exponential forms of equations and their equivalent log forms. Here are some examples, and then you're going to practice. Well, simply put, guys, we need to be able to go from log to exponential. So here's some brief examples. The first one is log base 2. Log base 2 of x equals 3. Well, if you implement your log loop, you get 2 to the third power. 2 to the third equals x. Therefore, x equals 8. All right. Same drill. 1/2 is your base, so 1/2 to the fourth power is equal to x. And here's one that you should probably try and pause the video and try it on your own. 3 to the x power, that's going to equal 1 over 9. Now, let's go backwards. How do I go from 2 to the x equals 16, put it into log form? I said earlier, start with your base. If the base of the exponential function is 2, then the base of my logarithm is also 2. Picture your log loop now. Your log loop would start from 2 and be raised to what power? The x power. So we're going to write equals x, because if I were to draw my arrow, it would go 2 to the power of x. Whoops, I need an eraser, there we go. 2 to the power of x, and that's going to equal the number on the other side of the equal sign. So 2 to the x equals 16. That's how you go from exponential form back into log form. And then here are some other examples that you can practice on your own. X to the second power equals 1 over 64. Okay, we have our log base x of 4/3 equals 81. Remember, guys, this number here is your exponent. That number there will always be your exponent. And so when you're looking to go from exponential back into log form, you want to first notice the base, but then notice the exponent. That number goes on the outside. All right, so here we have a page that asks you to try going from log form into exponential form, but after you do that, they want you to go ahead and solve these. So not necessarily will it be in every problem that says, hey, solve these logs. No, not necessarily. What they will be asking of you is to, whenever you see things like this that can be solved, you simplify them. In other words, if you see log base 5 of 5 within the context of any problem, you should simply take that logarithm and replace it with a number. What number are we going to replace it with? Well, if we rewrite in exponential form 5 to the x equals 5, well, 5 to the x equals 5 to the 1, therefore x equals 1. So in the context of any problem, if you saw log base 5 of 5, you should replace that logarithm with 1. And we found out that exponential equations are inverse relationships with those logarithms. So when you simplify these, you're really looking for that exponent. Okay, let's try the next one. Log base 5 of 5 to the 4th power. Well, 5 to what power equals 5 to the 4? Common bases, exponents equal one another. Log base 4 of 2. What power do I need to raise 4 to get 2? Well, this is kind of interesting now, because 4 to the 0 power is 1, 4 to the 1 power is 4. We need to figure out how we can create common bases. Well, 4 has a common base of 2 squared. To the x, to the x power equals 2. Furthermore, we can take 2 and x and multiply them. 2 to the 2x equals 2 to the 1. If you are missing an exponent, it is 1. Therefore, we can say that the exponents are equal to one another now, and x equals 1/2. And that makes sense. We just learned in the previous unit that if you have 4 to the 1/2 power, that means the square root of 4, which is 2, and we're good to go. Let's look at this last one now. 3 to what power gives you 1 over 27? 3 to what power gives you 1 over 27? Well, 3 to the x, we could set that equal to 3 to the negative 3. Whenever you see 1 divided by, it typically will translate into negative exponents. And last but not least, what we need to cover here, guys, is graphing logarithms. Now, we graphed exponential equations back in 7-1. It's the same drill here. Essentially, we're going to make our XY table charts, but this time, because logs and exponential functions are inverse relationships, inverse functions of one another, what we're going to do is we're going to, instead of plug in values for x in our XY chart, we will plug in values -1, 0, and 1 in for y. Okay. So here are the characteristics. The domain and range have been now flipped around. The domain was all real numbers and exponential functions. It is now restricted to all positive real numbers because the asymptote, that barrier, that line that the function approaches but never crosses over for now, is in this case x equals 0, which is the y-axis, whereas before it was y equals 0 and it acted as the x-axis. So we're gonna mess around with these a little bit, and again, based off the base, that's what gives the orientation of the graph for now until we again introduce a, h, and k. So let's try to graph a few of these basic logs. All right. So if we're asked to graph the log base 5 of x, what we will do is the first thing we will do is rewrite as an exponential equation. In that we have 5 to the y equals x, and I want to point this out. You see right here, f of x and y, they are the same thing, just different notations. F of x is function notation, y is simply the dependent variable here. So don't get too caught up in that. When we ask you to rewrite as an exponential equation, because we're going to be putting these x's and y's as ordered pairs in the table, the t-charts, we want you to replace f of x with y. So here we are, step 1, f using my log loop. And it's kind of interesting too because we're going the other direction now, right? We're kind of going backwards, if you will, but it's still there. It's still the same thing, 5 to the y equals x. And then we will find easy ordered pairs, and those easy ordered pairs will come with those 3 similar values that you're kind of used to now from 7-1, but notice they're not in the x column, they will be in the y column. And then we'll go ahead and graph the points and make a note of where our asymptote is, and we'll go ahead and graph. So let's try one here. We will graph f of x equals the log base 1/3 of x. And so the first thing we'll do is we'll rewrite it with y, log base 1/3 to the x. Okay, 1/3 of x, excuse me. Now, let's make our t-chart. Here's our t-chart. And we're going to use those 3 values, -1, 0, and 1, but we're going to put it in the y column. And we will go ahead and now rewrite one-third to the y power equals x. So going from log form to exponential form, now we can plug in these values for y, which is now the exponent, and see what kind of input values, if you will, we'll get for x. So we're kind of doing inverse operations here. Don't get confused by it. Simply follow the 3 steps, and you will be able to graph any of these log functions. So here we go. -1. If I plug in -1 for y, 1/3 of the -1 equals 3. Okay, remember, 1 over 1/3 translates to 3. 1/3 to the 0 is 1, and then 1/3 to the 1 power is 1/3. Now, we have a barrier. Our barrier is this x-axis. I don't like that. Can I? Nah, that's alright. That'll work for now. Actually, it will not work. Apologies, guys. Moving on here. I'm going to replace it with a blue line here. So we have an asymptote at x equals 0. That's x equals 0, and that's in the asymptote. Now let's plot these ordered pairs. These ones right here. 3, -1. 1, 2, 3, -1 is here. 1, 0 is here. And then 1/3, we go all the way up to 1 here. Let's see if I can make it happen. That'll have to be good enough here. And then let's go ahead and plot our graph to the best of your abilities, of course. And there we are. There we are. Okay. I think it's safe to say that we need to now talk about domain and range. The domain is all positive real numbers because nothing to the left gets included on our graph because of our wall, our barrier, our asymptote. Notice too that the 0 has a parenthesis and not a bracket because 0 is not included in our domain. The range is flipped around from the exponentials equations. It's now all the numbers because everything from bottom to top gets covered. All right, so follow those 3 steps and you should be able to graph all of these logarithms. Okay, 3 to the x. Rewrite exponential function. Use these 3 y values. Plug them in. Asymptote. Ordered pairs. And we have ourselves another logarithm. This time opening the other direction because of the base. The base is larger than 1. The orientation is this way. As x values increase, y values also increase, whereas before the base was 1/3 in between 0 and 1. Therefore, as x values increase, y values would then decrease. So it opens up in a different direction. Doesn't really affect our domain or our range for that matter. What will, however, affect our domain range are the AH and K values. So if you need to pause the video and kind of go back at this moment, please do. Alright, AH and K, guys, here they are. They have not changed one bit. It's just a new general function. A, H, and K. Left and right, up and down, and this reflects the orientation. If it's negative, if A is negative, it's going to flip. It's going to reflect over the x. If the absolute value of A is bigger than 1, we're going to stretch. If it's less than 1, we will compress. So this isn't anything new. In the similar fashion that we graph 7-1, I will graph logarithms with the XY table chart given the additional columns. All right, so here we go. We're going to start with the parent graph. Now the parent graph is the base, right? The base is log base 10. So that's what we will graph, or not graph, sorry. What we will do is in our table charts, we will create 3 ordered pairs with this parent function. So 10 to the y, using your log loop, 10 to the y equals x. Okay, and in my chart, -1, 0, and 1, just like before, plugging these values in, I get 1/10, 1, and then 10. Now I would go ahead and graph this function with my asymptote of x equals 0 and call it a day. Domain would be all positive reals, and the range would be all real numbers. But now we have A, H, and K. We have transformations. And as we pointed out before, the values affected by the y are A and K, and the values affected with the horizontal shifts is the H value. So let's take a look at H. We'll notice that X is all by itself. There is no H value. For there to be a quantity or a shift horizontally, there would have to be some sort of quantity, X with a set of parentheses, -2, +5, whatever. It would have to be in a set of parentheses, but because of the missing parentheses, we're simply going to rewrite all of these X values. Now the Y, there is an A value and a K value. So here's A, H, and K. Now A is 3. We will take every Y value in this Y column, multiply it by A, and then add or subtract the K value. So 3 times y plus 1, that'll give us our new y coordinates for our ordered pairs. -1 times 3 is -3, -3 plus 1 is -2. So this is an ordered pair now, 1/10, comma, -2. The next one is 3 times 0 plus 1. The next one is 1, 1, and then 3 times 1 is 3. Plus 1 more gives you 4. So these are the 3 ordered pairs you should graph. 1/10, -2. So it's very, very little there. 1, 1 is here. And then 10 comma 4 is way over here. That's 3, here's 4. Okay. And we would presume to draw our asymptote. The asymptote is your h value. But because h is 0 here, it remains the vertical y-axis. If that said x plus 1 and everything in our column got shifted to the left by 1, we would also shift the horizontal asymptote 1 unit as well. So our domain and range will be the same for now until we have a horizontal shift. All right. Okay, here we go. This will be the last one for this video, but if you need more help, always come in and ask us. The log base 1/4 of x, that is the parent graph. So we will say that 1/4 to the y power equals x, and we will create our t-chart with these same 3 values, and then extend our table, and let's find our a, h, and k. Now, in the previous example, h was 0, k is 0 in this case, so there will be no vertical shift up or down. There is now a horizontal shift of -3 units. X minus 3 translates to a translation to the right 3 units. So that means, guys, that my asymptote is now x equals 3. The vertical line, 1, 2, 3, x equals 3. So without doing anything else, we can plot our asymptote, or another, our barrier, if you will. All right. Let's figure this out now. Because of the shift 3 units to the right, we will take every x value and add 3 to it. So it was from 4, -1. It'll now shift 4 plus 3. It is now shifted over to the right 3 more times. Now 1/4 plus 3 is 3 1/4, or 3.25. Now, let's see. What did we say? A and K affect our y column. A is 1/2, so we will take every y value, multiply it by 1/2, but because k is 0, we will go ahead and just leave the 1/2 y. Half of -1 is -1/2. So that's the first order pair that we plot. 7, -1/2. The next one is still 0, 4, 0, and then we take 1/2 of 1, which is +1/2, and add 0 to it. So 3 1/4. 3 1/4, 1/2. Let's plot these ordered pairs. Hopefully they line up nicely with our asymptote, and then we connected our dots. 1, 2, 3, 4, 5, 6, 7. 7.5. -1/2 is somewhere right here. Okay, 4, 0, 1, 2, 3, 4. And then 3 1/4, 1, 2, 3 1/4, up to 1/2. So it looks compressed, and it should be because the absolute value of a is less than 1, so it does look compressed, and we will go ahead and flatten it out a little bit, and that makes sense to us, like I said, because of the a value of 1/2. The domain has been shifted 3 units to the right, therefore my domain gets written as so, 3, +infinity, and our range doesn't change because of the all real numbers that the y values cover. All right.